Welcome to our 10th lesson in the Engineering Design Process series. Today I'll be discussing the topic of risk analysis. Perhaps you're wondering why this is part of the design process, so hold on. Hopefully you'll see this by the end of our lesson today. I'm Denny Davis, retired professor of engineering education. It's my pleasure to lead this discussion today. Notice that risk analysis is the last step in what I've defined as this design process. So before we jump into risk analysis, let's remind ourselves of what we've accomplished so far. First, we identified needs for design based on a strategy of how we're going to use this final design solution. Then we identified ideas for the component parts of the solution. Next, we came up with an overall conceptual design, putting together the pieces to identify how the entire design would perform, how it would function, how it would accomplish the needs that we had identified earlier. Then, of course, we spent some time talking about prototyping and analyzing these prototypes. The information we gained from that we then applied to defining specific details of the solution. And last time we talked about how we need to consider certain practical issues about how we assemble the solution. And then we talked about methods and ways to consider, discuss, evaluate test results to determine how well we have met the needs that we set out to meet at the very beginning. So what remains to be done? Well, today we're going to identify potential failures that could occur with the design we're building, because some of these can be very costly. And then that will help us focus on improvements we can make, so we give the greatest value with our solution. So clearly what we're about to do today is identify the most serious risks of failures so that we can then come up with design improvements that will enable us to either avoid these failures or minimize the impact of such failures. So before we proceed, let's talk about a failure. What is a failure? We're talking about, in this case, developing a robot for competition. What is a failure? Many of these failures we think of would be characterized as mechanical failures. The chain might come off a drive wheel, the cord or chain or something might break. You might have something jam, and so in that case it fails to deploy as intended. Or maybe it's more like we pick up a game element from the wrong side, the wrong color, which is not allowed in the game. That's a failure as well. There are also electrical failures. Sometimes you have sensors that read something incorrectly. Sometimes we have static discharge build up, and then suddenly the discharge occurs and it shuts down our electronics. That's a serious failure. Sometimes it's just a matter of not paying proper attention to our battery charge, which falls to the point that things don't function as intended. There are also failures that are human failures. Perhaps the operator misjudges something. Because of that misjudgment, takes the wrong action. That's a failure. It could be the drive coach who's informing the driver of what to do and fails to inform the driver about something that is very important for what the driver is to do. That's a failure. You can see many different things can be considered a failure. It can have an impact on our performance. So therefore, we'll be considering a wide range of things as failures today. And with these failures, as you notice this list, you'll see that some of them seem to be much more serious than others. So we're going to be attempting to identify for potential failures what is their level of impact, or how impactful are they. So how important is it that we avoid that kind of failure? We probably come up with ways in which we characterize the most serious to the least serious, with titles that we might put on them, something like fatal or crippling, damaging, or maybe very minor. Then, of course, for each of the failures that we're considering, we would try to map those to the level of impact and give us some guidance as to which ones we need to address first. But there are actually some formal procedures to use. So I'm going to be discussing today a procedure for assessing the risk associated with different failures, so we can rank them in terms of the priority for which we should be addressing these risks. So what is a risk? Well, it's simply exposure to some kind of a undesirable circumstance that might result in injury, loss, danger, something. It's the possibility that something bad is going to happen. Why should we spend time? What's the value of analyzing these risks? Well, actually, it's more than you might think of at first. It impacts our decision making. With risk information, we can choose paths that would produce the lowest risk. It also affects how we control things, how we manage that risk, because if we know certain things cause higher risk, we can avoid those particular actions that could lead to higher risk. But in a larger setting, there's a whole mindset about design that considers risk all along the way. The National Institute for Occupational Safety and Health has identified what they call prevention through design. They're looking at ways in which we can reduce the risk by making good design decisions. Those lower the risk and prevent accidents, injuries, and serious consequences. So a whole mindset of thinking about reducing risk is important for those involved in engineering. What are the factors that go into defining the risk associated with a failure? There are three. One is called seriousness of the failure. In other words, how harmful is it if this failure occurs? What are its impacts? The second is a likeliness that this failure will occur. It's the probability that one could associate with this failure. The third is the ability to control or to prevent the failure, because there are times, situations in which we can anticipate the failure and we can avoid it. So these three factors come into play when we're defining the level of risk associated with a failure. We end up calculating what's called a risk priority number using these factors. We calculate it by multiplying scores associated with severity of the risk, the likelihood that it will occur, and our ability to control or prevent that risk. So it's a product of these three scores. The severity would be given a score from 1 to 10. 1 meaning that there's really no effect if this occurs. To 10, which is something very serious, and depending on the situation, It could be serious damage, it could be penalty assessed to you, it could be a serious injury. So severity is scored between 1 and 10. The likelihood of it occurring is given a score from 1 to 10. 1 meaning that it's nearly impossible for this to occur, to a 10, which means it's nearly certain to occur. And the control score from 1 to 10 considers whether it's something that's very almost certain that we could prevent it by taking certain action. That would be a 1. To a 10, which means it's almost impossible to prevent. There's nothing we can do to prevent it from occurring. So let's take a very quick example here. Let's say we're talking about a failure that is grabbing 2 game elements when only 1 is allowed. So our collection system is out there collecting, and it happens to grab 2 game elements. And the consequence of this could be that we would be assessed a 20-point penalty. So let's think then about the seriousness, the likelihood, and control. What would be an appropriate serious severity score? Well, you could, depending upon the situation, give it a score of 8, because if we're unable to avoid this occurrence and we are assessed a penalty, that 20-point penalty could be very serious in terms of its impact on our game success. The likelihood, well, it depends upon your past experience and seeing how often that happens. But let's say it's somewhere in the middle, moderately possible to occur. And then the controllability, well, based on knowing how this occurs, what happens leads up to its occurrence, we may have an ability to prevent it, maybe not. Let's say, though, in this case, we assess a score of 7, which means that we currently see it as somewhat difficult to prevent. We can't see it coming, and so therefore we're going to give it a score of 7. We then multiply these 3 scores together and get a score of 280. That's the risk priority number that we would assign to this particular type of failure. You wonder, well, is that good or bad? Well, with this kind of a scoring system, 1 to 10 for each of these 3 factors, anytime we get a risk priority number greater than 100, it's something that we should be taking seriously and take some action to reduce that risk or prevent that failure from occurring altogether. So RPN above 100 is of concern. So let's look more deeply into these 3 different factors. First, for severity of effect, you're going to need to adapt this for the particular situation you're in. So we are given some generic kinds of definitions which say no effect, very slight effect, and so on, associated with these different scores. And in the smaller italicized print, I've attempted to give you some examples of how you might characterize each of these levels of severity. So for instance, a score of 2, very slight effect, you might say, well, it's very slight, it looks bad, something didn't look like it worked well, but it really didn't have any effect on how things performed. So a 2 is appropriate. However, a 3, where it begins to slow down your performance, but again, it's not causing you to lose points or to shut down or anything serious. And then each of the successive numbers here, we identify conditions that we would call a minor effect, a moderate effect, significant effect, all the way up to something that's a very serious safety violation or dangerous condition for number 10. So these scores then need to be assessed based on your understanding of the game. Let's take 3 different examples here. Let's say one failure would be that the chain comes off. Chain that's turning the rotating paddles that pull rings into a collection system. And it comes off early in the game. So what severity might we, what score might we give it for severity? Well, maybe 6. It's a significant effect. If it comes off early, it's probably going to have an impact of over 10 points. Again, you have to consider the game and points and so on. But in this case, let's just say we give it a score of 6. How about a delivery linkage? And it moves and sometimes it sticks. You have to kind of back up and hit it again a second try before it functions properly. What would we say the severity is for this? Well, I might give it a 3 because it slows action. We have to do something a second time. It doesn't prevent the action. It doesn't probably have a serious impact. So we might give it a 3. What about an autonomous failure, where we send the robot off for a specified travel distance in order to get 2 points, but occasionally it ends up going too short of a distance? Well, okay, so if it comes up too short, then it can't score, can't get those 10 points. So perhaps we say it's a moderate effect because it's going to drop 10 points. So with that, then we have some better understanding of what that severity means. Let's do the same thing for the likelihood of failure. And here we're talking about failure in a match. We're not talking about failure in our practice field and so on. But in a match, if it occurs, we're talking about that as a failure. So again, we have definitions for scores from 1 to 10. From something nearly impossible to occur, that remote chance, very slight chance, and all the way up to nearly certain to occur. Let's take those same 3 examples and think about what kind of a likelihood score we might use. Chain coming off, well, again, this is going to come from your experience in your practice. You may say, well, there's a slight chance of occurring. It occurs every now and then, but not very often. Okay, so I'll give it 4. What about the delivery linkage sticking? Again, how often have you seen that happen? Maybe there's a moderate chance of occurring. What about the autonomous travel? Now you should have some data, some experience that will help you identify how frequently that occurs. And maybe it's a low chance of occurring, but it does occur, and so I may give it a 5. So again, we have to pick these numbers. It's quite subjective, but the more experience you have with your assembled design gives you a better ability to assign some likelihood scores in this risk assessment. Now for controlling so that we can prevent failure from occurring, again we're talking about failure occurring in a match, the things that we can actually do to prevent them. And our control scores range from 1, where it's almost certain that we can prevent it, we can see it coming, we can avoid it, to 10, where it doesn't matter what we try, there's nothing we can do to prevent it. Again, let's take those 3 examples. The chain comes off. How controllable is it that we could prevent that? Well, I might give it a 5. There may be a chance of preventing it because we know that in certain approaches to collecting our game elements, it makes the paddle more susceptible to higher forces. and therefore the chain pops off. So again, by experience, we might say there was a moderate chance that we could prevent it just by avoiding those situations. For the delivery that sticks, again, our experience might guide us in this, and we can say there's a moderate chance. We know that if we go at it a certain way, we're less likely for that to occur. So again, we make a judgment on that. The autonomous travel, this one, once you turn a robot loose, there's nothing you can do, so it's going to happen or not happen. And maybe there's some slight ability that you can, in the way you position the robot, set it up before you start autonomous, that you can affect how and whether this failure occurs, whether it's going to go too short of a distance. So in this case, I might say it's a very slight chance we could prevent it. Maybe there's a little bit of a chance, but probably not much we can do about it. So again, we choose these control scores based upon our experience and understanding of what the robot must do. So then we calculate the risk priority number. That's the product of the severity times likelihood score times control score. And let's take those examples. The chain comes off early. We had given it a score of 6 for severity, 4 for likelihood, and 5 for control. Gives us a RPN score of 120. The delivery failure we talked about, the RPN here, the severity was much less, the likelihood was a little bit higher, and the controllability was the same. We get a score here of 90. In the autonomous one, what hurts us here again is that lack of ability to control it. And so we end up with 5 times 5 times 8 and a score of 200. Now, once we have a series of potential failures scored with risk priority numbers, that should allow us to make some conclusions about the different types of failures. Looking at the collection chain, that's the one with the chain coming off. We'll probably, because it had a score of 120, we probably should tackle that problem. Okay. The delivery sticking is tolerable. It's not really causing us much difficulty, so we probably don't need to deal with that one, at least not right away. But the autonomous travel one, note that that's the one with the highest RPN number. It clearly needs to be fixed. And so one would need to go back to the drawing board and determine how can we avoid having that failure from occurring. I would suggest in this case you probably need a control system with a sensor so that will enable us to have reliable travel distances. So let's take another situation. We're looking at the ring scoring, and we're going to assess the different kinds of risks that might occur for this particular system. So let's assume that in our design team we have a subgroup that's focused on this collection. They have a collection system that uses these rotating fingers to grab a ring, pull it into the scoop, and then from there they'll handle it for scoring. So they're looking at what are the possible kinds of failures that would occur in the collection. Okay. Maybe they've come up with a list of failures, possible failures. Here I've identified 4 that might be among those that they would consider. So for each of these, you'd want to assign a score for the severity, the likelihood, and control. Let's say that the fingers do not catch the ring to pull it in. Okay, the severity here is a low score because you may fail, but by readjusting, going at it a second time, you probably have the opportunity you've lost a little bit of time, but you probably have not prevented yourself from scoring. Likelihood, that could be by experience seeing that it's going to occur more frequently. Controllability, well, there's some ability to control by the approach you use coming toward the ring for collection. So that gives us an RPM of 90. What about the wrong color game element? So we went after, say, a red one, but we happen to pick up a blue one. Well, that's pretty severe because it probably ends up costing us a penalty. Likelihood, perhaps it's not as likely. Controllability, again, depends upon our operators being on top of it and avoiding those conditions. So we could perhaps have a score of 120 here. Fingers might actually throw the ring into the scoop, but throw it up and over and out of the scoop. And so I've assigned some numbers here that might be appropriate. And then the drive chain issue again. Here it would be severe because it would, if it's early in the game, it could keep us from picking up rings in the future for the rest of the game and so on. Controllability is low, difficult to control that one. So again, we give it an 8 in this case, and RPM is 288. So when you're given a list of these failures, you've determined RPMs, then the design team, who has the best understanding of these failures, sets about to choose what to do. So based on the scores, the drive chain is the failure that has the highest RPM, so you would tackle that one first. And perhaps you decide you're going to fix the alignment and adjust the chain tension to keep the chain on. So you know there's some actions you can take, and you set about giving it a priority to get that done. The next one, next highest score, was the wrong color. That could be addressed by installing a sensor to detect the color, and if it's a wrong color, to quickly eject it so that it is ejected before you're assessed a penalty. And the third in order would be the fingers throwing the ring beyond the scoop, and so you'd address that perhaps by a baffle or some other way. So you go back, you study the problem, what's causing the problem, make a design change so that at the end of this risk assessment and design modification, we have a design that's going to perform much more reliably with fewer costly failures. So let's summarize what we've learned about risk analysis. Number one, there are motivations for risk assessment. We can probably group them all by saying preventing costly failures, failures that could cause you to lose a match, hurt someone, seriously damage a robot, etc. So we're motivated to avoid those costly failures. We identify those potential failures, many of which are going to be mechanical, they're going to be electrical, electronic, but don't forget that some of them could be operator cost. Think about what the operator can do, has done in the past, so that you recognize those as failures and figure out how to avoid those. For each of those failures, calculate the RPM, which means you have to guess at a score for severity, likelihood, control, and then respond to the assessment. Give attention to the failures in priority order. The highest RPM scores really should be addressed first. And consider design refinements that are going to lower the seriousness, yes. So perhaps you can make it so that when something fails, it's not going to be as costly. You can consider the use of sensors to lower the likelihood so that the sensor can detect and prevent some of these from happening. Or perhaps you need to consider training and practice of your drive team in order to improve the controls. So they understand, they can anticipate what's happening, they can actually take actions to prevent the failures from occurring. In reality, what we really need to do is put on our thinking cap and think risk analysis as we go through design, identifying those possible failures and finding ways to prevent the failures from occurring. So we've gone through this engineering design process lesson series, quite a number of different lessons that we've addressed. And by going through this process, you should now have a wise game strategy really based upon your understanding of the game and what you want to do, and this drives your definition of needs. So knowing what you must do, you've defined the appropriate needs that drive the design of your solution. Then, hopefully, we've come up with many varied ideas to start the process, many creative and high potential ideas, and the high potential ideas will begin to come to the surface, and we put them together into a conceptual design, which is the overall design, the main concepts for how we're going to accomplish the different functions, and they all work together effectively. Then we establish requirements based upon those concepts. You've probably then done a large amount of prototyping and analysis in order to really understand how the concepts work and how to optimize those. This leads to design details based on your knowledge of how things operate. So it's knowledge-based detailing of the design. And then we've talked about assembly, thinking about how the robot, your solution, is going to be used to make sure that it's useful. We've talked about evaluating with regard to what the user needs, getting good data, making good evaluations so you can prove the performance of your design solution. And finally, we've looked at risk analysis so that we can take this design that has the potential to meet the user's needs, but now we're preventing it from failing so that it does reliably meet those needs. That is the pinnacle of a good engineering design. It meets the needs and it will do it reliably. So we've ended up, by going through this series, we've developed an efficient design process which hopefully keeps you from going back, repeating steps multiple times, so you have fewer iterations and makes your design process more efficient. We've also developed a solution that is driven by the strategy from the very beginning. So it provides us what is needed and not just what we thought was cool and we want to produce based on our own selfish desires. And finally, with this good risk analysis and improvement, we have a durable solution, one that has few failures, and hopefully those failures that remain are going to be low impact failures. So I encourage you to take this engineering design process seriously, giving proper attention to each of these steps, moving through it efficiently and effectively to get to this kind of quality solution in the end. Before we end, I'd just like to acknowledge first an FTC program that really have provided us the context, the motivation for doing engineering design and doing it in a gracious way. I'd like to thank the Roborators and experts and their teams and their coaches for motivating this series, but also helping to launch this series with their participation. Note that Severity Design Learning has then created these lessons, and along with the lessons there's a pre-engineering primer, second edition, that both of these are available to teams to learn engineering. You can find more information on my website, veritydesignlearning.com. All the video lessons of the series are available from the Roborators YouTube channel under a playlist called Engineering Design Process Lessons. Thank you for being part of this series. I hope it's been of great value to you. I hope you promote it and share it with others who are involved in similar kinds of activities, learning to do engineering, and hopefully learning the engineering design process, how to implement it effectively. Thank you for participating with us in this series.